Hello everyone, this is the video lecture of section 8.2, second part. Okay, we started 8.2, the concept of convergence of series, infinite series, in first part, and then we got the most important and basic kind of convergence series, that is geometric series with common ratio between -1 and 1. Now, we will begin the second part of the section with the second group of convergence series, that is telescoping series. Example 4, section 8.2, example 4. Determine the convergence of the series A, I from 1 to infinity, 1 over I times I plus 1. I from 1 to infinity, 1 over I times I plus 2. Okay? Alright. So, again, sum of infinite series, if it converges, is the limit of partial sum sequence Sn, or running total sequence. So we have to find out what is, this is the partial sum. Now, obviously this is 1 times 2, 2 times 3, 3 times 4, all the way to n plus 1. Now, you remember the partial fraction? If you do this, you will find that this is going to be 1 over x minus 1 over x plus 1. Okay? So if you combine it, x plus 1 over x plus 1, x over x, x cancel, 1 over x times x plus 1. Just like that. This one is 1 over I. You can write it, this is 1 over I minus 1 over I plus 1, which is 1 over 1 minus 1 half. I'm going to write here 1 half. Okay? I equals 2 minus 1/3, 1/3 minus 1/4. All the way n minus n. So if you ask them up, oh, what is that? The middle terms cancel all the way, except for the very first term minus very last. Okay? So, the infinite series, sum of the infinite series, by definition, is the limit of partial sum sequence, limit of running total, which is 1 minus 1 over n. Constant 1 stays constant 1, 1 over n approaches 0. Hey, this one approaches 1. 1 half plus 1 6 plus 1 12. It's going to approach 1. Okay? What is the price? We call this kind of series as telescoping series because, look at this. You can have this long form, you can shorten. Just like you are extending telescope and contract, put it back. Right? Extend, contract. Just like telescope. You can add and subtract, extend it, or cancel, contract to only 2 times. Right? So that's why we call it telescoping series. The next one, now, your Sn is I from 1 through n infinity. 1 over I plus 2. Again, if you do this, you'll find that A equals 1/2, B equals -1/2, actually. You can find it. 1/2 times x plus 2 will be 1/2 x plus 1 minus 1/2 of x. Cancels and 1 remains. Or you can write it, this one, as 1/2 out, 1 over x plus 1 over I minus 1 over I plus 2. If you combine them together, you will see common denominator I plus 1, I plus 2, I plus 2, I over I, and I plus 2 minus I. So 2 over I times I plus 2. That 2 cancel with this. So we'll get this. Alright. So this is, you can take 1/2 out of the sigma. Equals 1/2. Alright? And then this one is big brace. 1 over 1 minus 1/3. Right? This one. And 1/2 minus 1/4. 1/3 minus 1/5. 1/4 minus 1/6. All of the way. 1 over n minus 3. N minus 2 minus 1 over n. 1 over n minus 1 minus 1 over n plus 1. 1 over n minus 1 over n plus 2. Okay? 1 over 1, 1 over 2 is nothing. 2 cancel with, but minus 1/3. Finding this. Minus 1/4 finding. Minus 1/5 will be over here. So, minus, subtraction starting from minus 1/3, minus 1/4. That's why the first two positive terms, 1 over 1, 1/2 survives. Everything else cancel each other. On the other hand, this one will be cancelled. But then, among the positive terms, nothing to be cancelled with 1 over n plus 1. This is it. So these two survives, but this one will be cancelled over here. This one will be cancelled way over there, somewhere. Alright? So the first two positive terms survives. Last two negative terms survive. So what do you have? 1/2. 1 plus 1/2, which is 3 over 2 minus 1 over n plus 1 minus. This is it. I'm not going to even combine this because limit will be 0 anyway. So infinite series 1 to infinity 1 over I times I plus 2. This one is limit n goes to infinity Sn, which is 1/2 3 over 2 minus 1 over n plus 1. And this one goes to 0, this one goes to 0. 3 over 4. So it'll approach 3 over 4. Okay? So this is another telescope. You can extend, contract, telescoping series. Most of the inside terms can be cancelled using partial fraction techniques. Okay? Telescoping series. Now, so we learn two different types of convergence series. One is geometric series with common ratio whose absolute value is less than 1, and this kind of telescoping series. Now, there are also important series which is not convergent. The first example is harmonic series. 1 to infinity. 1 over n. 1/3, 1/4, 1/5. Keep going. Now, this is called harmonic series. Okay? If you use calculator, if you add from 1 to 1/10, it's gonna be around 3 something. If you add all the way to 100, around 6 something. If you add all the way to 1,000, it'll be around, around 9 or 10. even after 1,000 terms. Then you might be led to believe that maybe it is convergent because it grows so little. Maybe it is convergent some finite value. But the interesting thing is that the amount you grow in running total from 1 to the 10th term, around 3 something. And from there up to 100 terms, from 3 to 6. 100 to 1,000 terms, 3 to 9. So, if you cover 10 more times terms each time, you'll grow by the same amount. Right? The first 10 terms, 100 terms, 1,000 terms, 10,000 terms, 100,000 terms, million terms. Then you will rise more or less steadily. If you cover 10 more times terms, 10 times more terms, that is logarithmic growth, right? It turns out that this one goes to infinity. Slowly, just like ln of x star. Very closely follow ln of x. And you will see why this one closely follows ln of x in the next section, integral test. But here we will prove this one using even more elementary techniques. Same idea as I just said. S2, 1 plus 1 half. S4. Now, I'm going to group it like this. 1 and 1 half. So this one is greater than, look at this, 1 half. I'm gonna, 1/3 is larger than 1/4, right? So you have another 1 half together. So 1 plus 1 half times 2. I'm gonna write it that way. S8. 1/4, 1/5, 6, 7, 8. This time, see, 2, 4, 6. I'm gonna parenthesize 1, 2, and 4. This one will be greater than, look at this. I'll make it all the last terms. Obviously, this is greater than 1/4. The whole thing is greater than this. And also this one, greater than all smallest one. Right? Why did I do that? Then this is 2 times 1/4, 1 half. Another 1 half. So it is 1 plus 1 half times 3. And you can get now you get the idea, right? 16. 1/5 all the way to 1/8. 1/9 all the way to 1/16, which is greater than 1, 1 half, 1/4, 1/4, 1/8 all the way, and 1/16 all the way. This is 8 terms. This is 2, 4, 8 terms. So this is add up to be 1 half. Add up to be 1 half. 8 times 1/16. So this is, so 16 is greater than 1 plus 1 half times 4. What is it? 16 is as 2 to the 4th, 2 to the 3rd, 2 to the 2nd, right? So what is it? S of 2 to the nth. If you cover 2 to the nth term, this will be n/1 plus n/2. Well, n goes to infinity means this n goes to infinity. If you want to cover the whole terms, anyway, this n goes to infinity. This one goes to infinity as n goes to infinity. That's why we can say that. As if you don't want, this is m, let's say m. M goes to infinity, infinity. So I call it m. Alright? So that's why it is divergent. Divergent series. Okay? So more or less, if you go twice many more terms each time, you grow steadily. Okay, logarithmic increase. Okay, so this is a very important example because your AN, even though the sequence itself going to 0, even though you're adding smaller and smaller, the terms you're adding is getting close and close to 0, yet the running total can go to infinity, keep growing, even though slowing down, but still going up and up and up and up. All right? Okay, before we continue, let me check the recording. All right. Next, also some important theorem. So relationship between this one and convergence series. This is theorem. If the series converges, then limit of AN not only exists, but it has to be 0. This is very important here. So you can call if this is hypothesis, this is conclusion. If P and Q structure. Now, if we can show this one, well, I'm going to show this one first, proof, and then I want to cover contrapositive. Okay. So suppose that, to prove this, suppose that this series, going to infinity, converges. What does it mean? I.e., limit of Sn, let's say S exists. Limit of partial sum sequence, limit of running total exists. And I'm going to call it S. Okay? That's our assumption. Now, can you isn't it obvious? A1 through AN minus A1 through AN minus all cancel, AN is remaining, right? Which means this is Sn minus 1 for all n greater than or equal to 2. Okay? Then limit of AN, we want to know what the limit is if it exists. The series being convergent means that this AN converges to S. Sn minus 1 is the same sequence, just one step behind. As n goes to infinity, this will approach the same value, right? Just one step behind, but your n goes to infinity. So, both convergent series, actually same series, one step behind. And those are, we learned that these two converge to the same value as just one step behind. Section 8.1 we already covered. S minus S 0, as we expect. Very important remark. The converse is not true. When you have a conditional statement, if P then Q, the converse statement is this. If Q then P, you are switching hypothesis and conclusion. If limit AN goes to 0, then this is one of the most prevalent confusion, misunderstanding. It is so tempting to believe that if AN goes to 0, you're adding almost to 0. each time. It must be convergent. No, it's not true. Some of them, yes, true, some of them is not, so it's not true in general. Counterexample. Just learn it. Even though an approaches 0, the whole series is divergent. Okay? Harmonic series. Harmonic series is a counterexample. However, we can use this theorem in a contrapositive way. We call it divergence. So what is contrapositive? If P then Q, then if not Q, then not P. Switch and then negate both. Like this one. If it is raining, then it is cloudy. Generally, it's a true statement. If it is not cloudy, then it is not raining. Think about it. If it is not cloudy, yeah, it cannot be raining. So original condition statement and its contrapositive are equivalent. Equivalent means that they both have the same truth value, either both true or both false. It can't be like true condition statement, false contrapositive. Either one of them is true, then the other is true. If one of them is false, then the other must be false too. They are equivalent. The contrapositive statement is what we call divergence test, correlated to divergence. Divergence test. So contrapositive of this one. If not Q, that means if limit of n either does not exist. See? The negation, anything other than limit 0 means either limit doesn't exist, or even though the limit exists, it's not going to be 0, right? Or even though limit exists, but it's not 0. Then this corresponding series diverges. Okay? So this will be so-called not Q. This is not P. Not convergent means divergent. Not P, right? Contrapositive, this one. So sometimes proving a series divergence is as easy as proving limit of an is not 0. Okay? So let's do an example. Okay. Example 5. Determine the convergence of this series n plus 1 squared over n times 2n plus 1. Okay? This is a perfect example for this divergence test because your an, this is your an, right? If you take the limit, what is it? N squared plus 2n plus 1 over 2n squared plus n. When you have a, just like x squared plus 2x plus 1 over 2x squared plus x. Well, these are dominant terms, will dominate over these lower power terms. This is basically one of n squared over 2n squared 1/2, which is not 0. By this, by divergence theorem, this series is divergent. Diverges. Okay. Finally, if theorem 3, if series converge, then the following series also converges. Can take C out of the infinite series. We prove this statement when you have I equals 1 through n. If you have a finite sum, yes, this is just a constant factor out. Basically, backward reading of distributive law. Splitting sigma notation over plus is just the associative law and commutative law addition. If it were a finite number, this was already done in basic. An interesting thing is this one works taking a constant out, works even you have infinite maintenance. So common factor factoring is working as long as this series are convergent. Okay? This one can be proven easily by using the definition. What does it mean by convergence of this series? Sn, right? Partial sum sequence Sn has a limit. I'm going to call it partial sum sequence of Dn as Tn. Tn converges. This will be S times C times Sn. Limit C can be taken out of the limit. So the limit property, constant multiple, can be taken out. An plus Bn, just Sn plus Tn will be your partial sum sequence. Limit of that can be split over addition. So these are basic, easy ones. If you go back to the definition of convergence of limit as a convergence of the series as a limit of partial sum sequence. So using this, we can finish the following theorem. This is so-called linear properties of infinite series notation. Find the sum of the following series. That is, and from 1 to infinity. All right. First of all, we learned that this is telescoping series, and that was 1 from example 4a, the beginning of today's lesson, right? And this one, just like previous lesson, section 8.2 is part 1, you can rewrite it 2 to the n, 3 to the first, 3 to the negative n. This is 3 times 2 to the n, 1/3 to the n, 2/3 to the n. So this is also convergent because your common ratio 2/3, absolute n is less than 1. And this is common, the first term, n equals 1, a over 1 minus r, a equals 2, 1 minus r. This is 1/3, 2 divided by 1/3, 2 times 3, 6. Okay? Now, it turns out that I'm going to call it this is series. Okay, S. S is, you can rewrite it, minus 2 times 1 over n times n plus 1. Plus, you can consider this constant times this series. So we learned that this sigma infinite series can be split over addition, right? Because both of them are convergent series. Constant times convergent series is also a convergent series. And this one can be taken out. We already found that this is 6. This is -2 times 1 So it is 4. Okay? So now this is the end of the section 8.2. All right? And section 8.2. So next time we will cover 8.3, which is integral test. This is so-called beginning of the more advanced test of convergence series. Okay. All right. This is the end of 8.2. I'll see you next time. Bye.